Welcome to the lecture on relations of set elements. To participate in this lecture, you need a basic understanding of set theory. In this chapter, we are going to define binary relations in sets, examine function as a binary relation, represent relations graphically through a matrix, to describe properties of relations, which are reflexive, symmetry, anti-symmetry, and transitive, to determine properties of a relation, and to determine the equivalence of relations. First of all, let's define what relation is in the context of set theory. A relation is an association or connection between the elements of one set to another. Look at the graphics. The first set on the left-hand side, set A, is a domain. It is connected to the second set, set B on the right-hand side, which we call codomain. So the source set is domain, the target set is codomain. The association or connection is between the elements of the domain set to the elements of the codomain set. This relationship can be written as an ordered pair. Example, A1, B1 is the first order pair connecting element A1 to element B1. The second ordered pair in this example is A2, B2, connecting element A2 to element B2. Let's look at one example. Suppose set A contains the element 1, 2, 3, and 4. And the second set, codomain set B, contains element 0, 2, 4, and 6. We can define connections between the elements in both sets. Graphically, we can draw the lines. This relationship is written as ARB, okay, A related to B. In this relationship, we can define the pattern or the constraint. In this example, it is that A is less than B. So we will map or we will connect all the elements in set A to add the elements in set B based on this constraint or pattern. Now let's do it together. Let's begin with the first element in set A, which is 1, and we will check against elements in set B one by one. First, we check against 0. It doesn't fulfill the constraint, which is that A is supposed to be less than B. Therefore, we don't draw the line. 1 to 2 fulfills the constraint whereby A is less than B. So is 4. So is element 6 in B. That's why we draw the lines from element 1 inside A to elements 2, 4, and 6 inside B. We repeat the same for the second element in set A, which is 2. We will check against one by one elements in B. 2 against 0, 2 against 2, 2 against 4. We only draw the line from 2 to 4 because this fulfills the criteria A less than B. And then 2 to 6. And then we repeat again for 3 and 4. These are the elements inside A against the other elements inside B. Now, how do we define the relations between A and B in a proposition format. First, give the relationship a name. In this example, we are using the letter R. Then, draw curly braces. First, we define the sets and the elements. And then after this type symbol, we'll define the constraint or the pattern of the relations. Now let's go through this together. The members of this set are ordered pairs, which contains A and B. What is A and B? Don't worry. A is an element of A, set A, yeah, and B is an element of set B. And they are, as given here, 1, 2, 3, 4 for set A and 0, 2, 4, 6 for set B. This A multiplies B is read as Cartesian product of domain set A and codomain set B. What it means is that the elements inside A is mapped with all the elements inside B. All the elements inside A will be mapped against all the elements inside B. But obviously, in this image, in this example, the mapping is not done to all, but to certain elements in set B because we need to fulfill the constraint given in the proposition. Okay, so the ordered pair is the ordered pairs are elements of all the possible connections between set A and set B. Now, this is how the answer look like graphically using Venn diagram of sets A and B. If we have to write down the answer in textual format, this is how we are going to write. Initially, the R is written as the formula. The answer will be written as follows. You see, these are the ordered pairs. One mapped to or connected to element 2, one connected to element 4, one connected to element 6, 2 connected to element 4, 2 connected to element 6, 3 connected to element 4, 3 connected to element 6, 4 connected to element 6. Again, 4 refers to the element inside A, whereas 6 refers to element inside B. Because it fulfills the criteria A less than B, yeah, 4 is less than 6. That's why it becomes a member of this relation set. So, what is binary relation? We have discussed about the definition of relation in set. But what is binary relation? Binary relation is a relation that connects objects of two different sets. How many sets do we have here? Two sets, which are A and B. Okay? Therefore, the relations, you see, the elements of the relation set will be ordered pair, not ordered ternary or ordered quaternary, only pair of two, because binary. Then what is not binary? Ternary relation, look at the members where we are identifying relations between three sets A, B, C, and then we have ternary ordered ternaries instead of ordered pairs. Yeah, quaternary, where we have 4 elements in the order rather than 2, and we can have more than 4. Yeah, any numbers, any number of elements that we want in the relation. So you have learned about function in high school. Typically, you have learned that function is used for mapping variable x to y. So in function x mapping to y, the function x is defined by a formula. Let's look at one example that probably you have learned in high school last time. The value of y is given by function x. So it is not something that you do not know. Yeah, you have learned about function. In this slide, I want to emphasize that function is actually a binary relation. Yeah, it is a binary relation. But it is a special binary relation because each input has only one output. Let's look at examples of this. We have a function that maps set A to set B. So what this means is we are mapping the elements inside set A to elements inside set B. Now this is a function because one input, okay, one input should only have one output. But in this case, obviously, it is not mapped to one output, but multiple outputs, because you see, from 1, it maps to 2, it also maps to 4, it also maps to 6. So this example is not a function, not function. It is a binary relation, but it's not a function. Okay, so let's look at examples. What is function? Now let's look at the first one. Here we can see that it's mapping 1 to 3. One input can only be mapped to one output. You see, strictly one output. So this is a function relation. Yeah, it is a binary relation, of course, but it's a function relation. Not all binary relation are not all binary relations are functions. Yeah, like in this example, the second example here, you see, one, the first input mapped to 1. Okay, fine. The second input 9 maps to 3 and -3. How many outputs here? 2 outputs, right? So this has violated the definition of function, which is to only one output. So this is not a function. It is a binary relation, but it's not a function. How about this one? This one looks like having multiple inputs to one output, right? So is this still considered a function? The answer is yes, because the definition says that only one output. Yeah, only one output. Doesn't say that multiple input is not allowed. Multiple input is allowed, but must be only one output. So this is a function. But the one on the right hand side here is not a function because it is many to many. So 1 to 1, many to 1 are functions. 1 to many, as long as the output is many, is not a function. Okay, let's move on to the next slide, moving away from function. The next slide is about the relation matrix. We can graphically represent the possible relations between two sets using relation matrix. Now, in this example here, yeah, we have two sets, yeah, set A and set B. Set A has elements X, Y, Z. Set B has elements 1, 2, 3. If we are to write this down in a propositional format, then this is how we do it. A is a set or list of elements X, Y, Z. B is a set or list of elements 1, 2, 3. And R here, check this out, is an empty set. R here is the relation set. It is empty because, as you can see here, there are no connections between the elements yet. Yeah, there are no connections between the elements yet. Okay. Now, we can represent this relation using the relation matrix. So the relation matrix is drawn as follows. How do we draw a relation matrix? Okay, so first of all, we need a grid. Yeah, a grid. So we need a 2D grid. Basically, it's a table. On the left-hand side, yeah, along the row, for the rows will be for the domains set. And then for the columns will be for the codomain set. In this example, the domain set is A for the rows, and the codomain is B for the columns. So we write down the elements of each. So for A, we have element X, Y, Z, which form the rows, and elements for codomain B will become the columns 1, 2, 3. All right. So the grids will be initially empty. If there's no relation between the domain and the codomain, then we will mark them as zeros. Yeah, meaning that there's no relation. So let's look at the first cell. Look at the first cell. In the first cell, the 0 here indicates that there is no relationship between X and 1. X is the element of A, and 1 is the element of B. Okay, there's no relationship. Now let's look at the second example here. The second example here says the relationship R1 is a cross product of set A and set B. Cross product means all the possible mappings, all the possible connections between A and B. So you look at the Venn diagram here, check this out. X is connected to all the elements of B, so is Y, so is Z. This is what we mean by cross product. Look at the relation matrix, it looks exactly the same. What is different here? Because all the elements in set A is connected to all the elements in set B. Therefore, we indicate that the presence by using number 1, okay, instead of 0. Now, in some books or some other materials, they may not use 0 or 1s. They may use false for 0, true for 1, or sometimes they use ticking, yeah, ticking X, ticking to indicate 1, X to indicate 0. So it's just a different notation convention, but it has the same meaning. So let's look at more example of this, reinforce our understanding of what relation matrix is and how to create one. Still the same Venn diagram, same set A and B. The only difference now is the relations, yeah, whereby element of set A is connected to only one element of set B. Okay, so this is a function, yeah, a function relation, only one output, but that does not matter. That is from the previous slide. Knowledge of function is not relevant here. Okay, what you need to know is how to draw the relation matrix. Okay, matrix here refers to the table or grid. Yeah, so you see the way we draw the frame of the matrix is the same. On the left-hand side, for the rows, it's always the domain. On the top side, for the columns, it's always the codomain, yeah, the target set. So we will populate the columns with the elements of B, and then we populate the row labels with elements from A. And then inside the grid cells, we put either 0 or 1 to indicate presence, to indicate absence or presence, respectively, of the connections between the elements. Now, in this case, look at here. For the first cell, X1, since there is a connector there, we will place 1 there. There is none to 2, element 2. There's none to element 3, so we put zeros. We repeat the same for other rows, other elements of A. This is how we do it, yeah, row by row. So this becomes the relation matrix R2, yeah, as given here. The name of the relation is R2 of A versus B, set A to set B. Okay, so you can try plotting the relation matrix for the following relations. You see, they are all based on the same sets A and B, but the relations are different as given by R3. These are the connections. Yeah. How do you plot them into here? Yeah, and then R4, another one. So I'll show a sample for R3, and you work out R4 on your own at your sweet time. So let's try R3. Okay, so this is how we populate the relation matrix. Let's begin with the first row, X. Okay, so X is connected to 3. X is connected to 3, so we put 1 there. Oops, sorry. And then, okay, moving on to the next one is Y connected to 2. So we go to the second row, Y, and look out for column 2. And then finally, the third ordered pair is row Z connected to 1. Okay, so this is how you produce the matrix for R3. And for the vacant or the empty cells, you can leave them there, and you can leave them empty, or you can just populate them with zeros because there are no connections between them. So on, some issues with my pointer, my stylus. So try what's going on. Okay, so that's the answer for R3. Okay, let's look at a different, let's look at another example. Example 1 with a different set. Set A with elements A members, elements are 0, 1, 2, and set B elements are A and B. And the other important information we need is the relation list or relation set. Okay, so here it's giving you ordered pairs linking elements from A to B. And there are 4 connections here, as you can see, 4 connections. 1, 2, 3, 4, as seen in the relation set. So the question asks you to draw the graphical representation of the relation using Venn diagram. What you do is use this information, A, set A, draw the Venn diagram of set A, and then draw the Venn diagram of set B, and then use the information on the relation R here to draw the lines. 0 to A, 1 to A, 0 to B, 2 to B. Okay, that's for the first question A. Then the second question, plot the relation matrix. Now, you can plot the relation matrix by referring to the Venn diagram you have done, or you can plot directly based on the information given above. First thing you need to know is on the row side, yeah, we need the elements from A, 0, 1, 2. And then on the column side, we need elements of set B, AB. And then here, as you can see, we're not using zeros or ones. Instead, we will tick if there's a relation. So 0A, there is a relation 1A, there's a relation. 0B, there's a relation. 2B, there is a relation. So the empty cells indicate no relation, or can just put X there if you want to. It doesn't really matter. If it's left empty, it indicates no connection, no relation. Yeah. Okay, let's look at example 2. Let's say A, the set A, instead of representing a set of numbers, now it is representing the set of students in your school. You can think of any of the friends' names, yeah? And then B, set of courses. And then let R be the relation that consists of those pairs A, B. So what is A and B here? These are the elements from the first lowercase a is the elements of set uppercase A, which is a set of students, and lowercase b here is an element of uppercase B, which is the set of courses, where A is a student enrolled and course B. Yeah, see the definition of A and B is given here. So given the relation, okay, so there are some instances or values of the ordered pairs. Jason enrolled in course CS518. Deborah enrolls in course CS518. Jason enrolls in course CS510. So this actually answers the first question A, identify the ordered pairs, okay, and write their meaning. You know, Jason, for the first ordered pair, Jason, CS518. It means Jason enrolled in course CS518. Okay, so repeat the same for others. Is the relation binary? Answer is yes, because as you can see, in the ordered pair, how many elements involved in the relation? Only 2 elements, right? So it's binary. Determine if the following statement is true or false. Deborah is also enrolled in CS510. Now check the relation. Do you have Deborah? She has taken CS. She is enrolled in CS518, but there's no CS510 for Deborah. So the answer is false, because it is not, for this particular ordered pair, taking 510, it is not an element of the relation here. Draw the relationship of the elements in domain A and codomain B. Okay, so the gist here is you first draw the domain, then draw the codomain, and you populate them with the elements, Jason, Deborah, and then you populate the set B with the other courses. Okay, and then you, referring to the relation here, you will plot them accordingly. Jason is taking both. Deborah is taking only 518. Yeah, so the answer should look like this. The answer should look like this. Mappings. Right. Then the second question is on the relation matrix. You need to be able to produce a relation matrix. You can use the information given here. Draw the rows and columns, and then the information here from the R to do the to fill up the cells with either 1 or 0. Okay, so see on the left hand side is domain. We have 2 values or 2 elements there, Jason and Deborah. And then in set B, we have 2 courses there, 518 and 510. And then the relationship R information is used to determine whether it's 1 or 0 in cell. Okay, next question. This time, the values of the set is different. It's 1, 2, 3, 4. Okay, so what is interesting about this example 3 is that there's only 1 set given here, only 1 set instead of 2 sets. Just now we were looking at examples with 2 sets, right? Set A and set B. So we still can establish the relations and draw the relation matrix even with just one set. So how do we do that? Yeah. So this one is interesting. You see, the relation is defined by the formula ordered pair AB, where A and B are elements of the same set. So that's why we only need one set here, set A, because the lowercase a and lowercase b, these two elements are actually from the same set A elements, 1, 2, 3, 4. And then the pattern or the constraint of the relation is given by this statement. A divides B. So what does divides mean? Okay, 4 divides 2. It's true because there's no balance, right? 3, does it divides 2? No, because there is a balance of 1. So 4 divides 2, yes. How about 2 divides 1? Yes. All right, because there's no balance. How about 3 divides 2? Okay, we are talking about we are talking about 3 divides 2. How about 3 divides 1? Nope, because yes, because we can divide nicely, right? So 3 divides 1. So that's what divides mean here. Okay. Identify the ordered pairs in relation R. So based on this formula, okay. So you have to help you, maybe you want to do something like this. They are both the same pair. This is how you do it systematically. You take the first element of A, you check against all the elements in the second set A, and then you repeat the same for all other elements of the domain set. You only keep the connections that are correct, that fulfills the criteria A divides B. Yeah, so you only draw the line. Yeah, here I just show you how we do the checking systematically. So you draw the line if it fulfills the criteria. You don't draw the line if it doesn't fulfill the criteria. Okay, so this is how the answer looks like. Yeah. You see, when you do the sketching somewhere else, then you'll be able to plot it, because then we'll be able to identify all the relations. A divides 1, 2 divides 1, 2 divides 2, 3 divides 1, 3 divides 3, 4, 1, 4, 2, and 4, 4. Because just now, you won't miss out any ordered pair because you have been checking it systematically against the first element against all other elements in the second, in the codomain, and you do the same, repeat the same for all the members of the domain set. Okay, then draw the relationships in Venn diagram. I have shown you just now, but of course here you only maintain the relations, only maintain the arrows that fulfill the criteria A divides B. Yeah, you see, 1 divides 1, correct. 2 divides 1, correct. 2 divides 2, correct. But 2 doesn't divide 3, right? That's why there's no connector between 2 and 3. Then the next question is plot the relations, the relation matrix. Okay, so on the top here, because you only have one set, right? Obviously, the elements will be the same. 1, 2, 3, 4. For the rows and columns, 1, 2, 3, 4, 1, 2, 3, 4. And then based on the relation information, okay, all this, based on this information, we set the values in the cells one by one, row by row. Yeah, first row, all the columns, second row, all the columns, third row, and finally fourth row. If there's no relation, you can either leave it empty or can just put 0 there. But if you put 0, you have to do it for all. Okay. Let's move on more on relation matrix. So when we have many relation matrices, right, you will start noticing that there are certain patterns of the ones and zeros. Okay, all right. And these patterns can be analyzed from the following perspective. Is the relation matrix reflexive or not? Okay, that's the first one. Is it symmetric? Is it transitive? Yeah. Is it anti-symmetric? Now, irreflexive basically means it doesn't fulfill the criteria of being reflexive. All right. So what is reflexive? Reflexive means, okay, if you look at the diagram, it means if you look at the diagonal cells from left to right, yeah, from top left to bottom right, if all of them is populated by one, all of them populated by one, then it is reflexive. Yeah, it means that every element is a set in a set is related to itself. So what does this mean? I think the best way to understand this is by looking at examples. Yeah, but keep referring back to the definition. Every element in a set is related to itself. Yeah, and it always happens along the diagonal line, top left to bottom right. Only these cells in the green over here. Then the second perspective of patterns in relation matrix is symmetric. So you look at the second example here. So imagine you draw a diagonal line cutting across the diagonal cells. So we are going to ignore the diagonal cells. We're going to ignore the diagonal cells. Like in this case, we're going to ignore them entirely. What we are interested in is the cells on the opposite ends. Like here, the opposite ends. Yeah. These are the opposite ends. Are these mirror reflections or not? Are the cells on the opposite ends, either side, are they reflections or not? Mirror reflections. If yes, for all, must be all, then it's symmetric. If any of the reflection fails, that means you don't have the opposite pair with the same value. Like for example, instead of having 0 in the reflection along the reflexive line, this is the reflexive line, the diagonal line. Yeah, there's no similar value on the other end, then it is not symmetric, even just one. And then anti-symmetric, okay, is related to symmetric, but not exactly the same thing here. The definition is given as follows. If two elements are related, okay, let's say A related to B, can we have B related to A? The answer is no. For anti-symmetric, if A is related to B, then B should not be related to A. The relationship should be only in one direction. Okay. As an analogy, Romeo loves Juliet. Does Juliet love Romeo? If Juliet loves Romeo, then it is symmetric because Romeo loves Juliet, Juliet loves Romeo. But this is not anti-symmetry. In anti-symmetry, it should be either Romeo loves Juliet, but Juliet does not love Romeo, or Juliet loves Romeo, but Romeo does not love Juliet. The relationship must only be one way, one direction. That is what we call anti-symmetrical. The last perspective of the pattern is called the last properties, yeah, of the relation matrix is transitive. So the idea of transitive is such that if there is a relationship between A and B, and there is a relationship between B and C, then is there a relationship between A to C? If there is an evidence of being transitive. And this must be true for all the relationships in the R set in order for the whole relation matrix to be considered transitive. So we look at this in detail by through some examples after this. So let's look at the first one, reflexive. As I mentioned earlier, given that we have one set, right? And then the relationship are between the elements of the same set. Yeah, as shown here. Yeah, there's only one set, set A. Okay, so the elements are A, which is any of the elements inside A, and then lowercase a, another set, another element of any of the elements inside set A, which are part of the relationship for every member. Okay, so here we are looking if there is a presence of similar, if there's a relationship between similar elements of the same set. Okay, let's look at, let's have it this way. Let's say set A has a member, has elements 1, 2, 3, 4. So if we put it on the matrix, it will be 1, 2, 3, 4. And then on the columns, also 1, 2, 3, 4. Now, check this out. You see, element 1 of domain, element 1 of codomain, element 2, element 2, element 3, element 3, element 4, element 4. All this will occur along this diagonal line, right? Along this diagonal line, which is represented by this ordered pair. Because you see, they're same. AA instead of AB, you know, if AB means different, it means different element. Because AA means the same element with the same value. You see, 1, 1, 2, 2, 3, 3, 4, 4, which will happen along this diagonal line, cells along this diagonal line, or this line, reflexive line as well. Yeah. So you see here, all the values are 1, therefore reflexive. But at any time you see across this diagonal line, you see that there's an absence here, right? So this is no longer reflexive. It fails. Must have all the values 1 inside the diagonal cells. How about those cells outside the diagonal or reflexive line? We don't care about them. Regardless of the values, they are not important to determine whether it is reflexive or not. So pretty straightforward, huh? So let's analyze this. Let's analyze this question. Consider the following relations on 1, 2, 3, 4. So all these relations R1, R2, R3, R4 are based on the same relation. Yeah, are based on the same set. So here we are using an anonymous set. So the anonymous set is containing the element 1, 2, 3, and 4. Okay, and in R1, you see, because it's a binary relation, so means that we have two similar sets. Yeah, two similar sets. 1, 2, 3, 4. Yeah, I draw it this way. Actually, it's referring to the same set because there are no two separate sets, just one set, one which contains 1, 2, 3, 4, and then the ordered pair is actually like 1 map to 1. For example, look at this one. First order pair is indicating 1 map to 1, but instead of drawing 1 map to 1 like this, which is hard to interpret, okay, I draw a separate drawing of the set so that we can say more obviously, like 1 to 1, 1 to 2, 2 to 1, so on and so forth. Okay, so using the same set, right? Let's say for question number 2, for R2, we can have different possible relations. Okay, so look at the second one. 1, 1, 1, 2, 2, 1, 1, 1, 1, 2, 2, 1. Okay, so these are the relations that occur for R2. Now, this is how we can understand what R1's R2 to R6 is. In case you are still grappling with the understanding of what R's1 and how they are related to the set. Okay, so drawing them may help you out with your understanding. But to identify whether it's reflexive or not, yeah, this kind of drawing alone is not sufficient. You need to draw the matrix. I said, let's do it for R2 because R2 is a smaller relation. Okay, R2. Okay, and then the elements here are from the set 1, 2, 3, 4. Okay, so let's look at R2 only. So I do the mapping. 1, 1, yes. 1, 2, 2, 1. Now look at, regardless of how you do the plotting, most important part of the matrix is the diagonal cells. So here you see 1, and then there are empty cells, right? These are obviously indicating no relations. So this is not reflexive, yeah, not reflexive. So let's look at the solutions for other relations R1 to R6. Okay, so just now we have looked at R2, but we haven't looked at R1, right? So for R1, as you can see here, we are just bordered by the diagonal line. You see, there's an absence here, right? So this is not reflexive. We have done this one. Let's look at R3. Again, let's look at the diagonal line. 1, 1, 1, 1. So it is reflexive. What about this side? Okay, this is the part you should not get yourself confused with. This side are the set elements, 1, 2, 3, 4. And this side is the other set elements, the other elements of the same set. Yeah, so we do the mapping between the rows and columns based on these values on the left and on top of the cell. You see, like this one, is there a value between 1 and 1? Yes. 1 and 2, 1 and 2. Yes, but you see, we actually are not bothered by what is happening outside the reflexive line. Okay. So this one, obviously, the first thing you need to do is to look at the reflexive line. So it's not reflexive. This is reflexive. This is not reflexive. Now, to think about this solution, right? If the question asks you to draw the matrix, obviously you need to draw it to get full marks. But if you just need to determine whether it is reflexive or not, there is actually a shortcut to that. Yeah, you notice or not? The diagonal cells, right? Are actually represented by ordered pairs, which are easily recognizable. And for example, this is cell 1, 1, cell 2, 2, cell 3, 3, cell 4, 4. Yeah. Now, in the case of R5, it is reflexive, right? So how do I tell without drawing the relation matrix for R5? Let's look at R5. You see, we have 1, 1, we have 2, 2, we have 3, 3, we have 4, 4. Any other numbers? No more, right? Because it's only 1, 2, 3, 4. So you see, we have 1, 1, 2, 2, 3, 3, 4, 4. Clearly indicates that these reflexive cells are populated. Therefore, it's reflexive. How about an example where it is not reflexive. Let's look at R4. You see, it's empty, right? Without drawing this, can I tell? The answer is yes. I'll be looking for 1, 1, 2, 2, 3, 3, 4, 4, which are absent from this list of R4, right? So it is not reflexive. Then the next one is symmetric relations. For symmetric relation, as I mentioned just now, the first thing that you must do immediately is the moment you draw or you get the relation matrix or table, right? You draw the diagonal line. Draw diagonal line. The cells along this diagonal line, or what we call them diagonal cells, we are going to ignore them. They are just reference point, yeah? So what we're interested in will be the opposite sides, yeah, the counterparts of each cell. So we have divided them into two sectors, right? Every cell of one sector will have its counterpart on the other sector. Okay, so we want to make sure that they are equivalent. The counterparts are equivalent. Now let's look at an example where it is symmetry. Like I mentioned, the value inside the diagonal cells are not important. You just ignore them. Whether it's 1 or 0, doesn't matter. We don't care about those. Yeah, you see, like this one, 1, 1, 1, 1 is reflexive, but this one is 1, 1, 0, 1. We don't care. We are just interested in the cells, the other cells on the opposite sides of the sectors of the reflexive line. Yeah, like this one, we have 1 and its counterpart 1. Okay, 0 and its counterpart 0, 1 and its counterpart 1, 0 and its counterpart 0, 1, 1, 0, 0. All of them, therefore symmetric. But why is this first relation matrix not symmetrical? Again, first thing you need to do, draw the diagonal line. Sorry, again, I have to draw and check the counterparts. Yes, 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 yes. Oh no, you see, this is the one that is not matching because this one is 1. The counterpart is 1, whereas on the other side is 0. So the moment you find one pair of cell not fulfilling the symmetrical property, the whole relation matrix is considered not symmetric. Okay, no need to check the rest already. So the opposite of symmetry is asymmetry. So just now we have seen example of asymmetry and symmetric. What I want to point out in this slide is that the representation of symmetry in a daily context. Okay, let's consider two people, John and Mary. Okay, John and Mary. Let's consider the relation is sibling of. Now, if John is sibling of Mary, isn't Mary also the sibling of John? You see, it's a two-way relationship, right? John, Mary. John is sibling of Mary. Mary is also sibling of John. So this is symmetrical, right? Because it is two-way relationship. Right? The relationship exists for both. So we can say that, okay, there is a relationship J to N, which gives value 1, and also there's a relationship from M to J. So let's say if John is not a sibling of Mary, therefore Mary is also not the sibling of John. There will be 0, 0. All right. So it's symmetrical. Now let's look at the daily example of asymmetry relation. Let's look at the relation older than. Still the same set of elements, John and Mary. Okay, John being the older brother. John is older than Mary. Can we say Mary older than John? Cannot be, right? Because if John is older than Mary, then Mary definitely is younger than John. It's not older than John. So you see, this relationship is only one way. John is older. Mary is not older than John. So John being older than Mary is one, true, but Mary being older than John is not true, right? So you see, you don't have the matching pair here, right? So therefore, it's not symmetrical. It is asymmetry. So now you have learned about symmetry and asymmetry. I want to move on to another concept called anti-symmetry or anti-symmetry. Anti-symmetry is not asymmetry. It's not the same idea. Yeah, so I need your attention here. Anti-symmetry is not asymmetry, totally different. So what is anti-symmetry? To put it simply, again, first you draw the diagonal line from top left to bottom right. So now we have two segments on the bottom left and the other segment on the top right, right? There's some cells belonging to both sides. Now, take note that the counterparts. See, this one is 1, 0. The second one is 1, 0. This one is 0, 1. Okay. And this one is 0, 1. Okay. 0, 0 we can ignore. So the key idea of anti-symmetry is that it must not have its counterpart. It must not have its counterpart. The relationship is only one way. The relationship is only one way. Yeah. For example, if Romeo loves Juliet, okay, but Juliet does not love Romeo, this is anti-symmetry. However, if Romeo doesn't love Juliet and Juliet loves Romeo, it's also anti-symmetry. If Romeo loves Juliet and Juliet also loves Romeo, not anti-symmetry. What about Romeo doesn't love Juliet or Juliet doesn't love Romeo? We don't consider this. Yeah, we don't consider this because there's no relationship at all in the first place. So consider the second example here, being anti-symmetry. Again, we draw the diagonal line separating bottom left segments and top right segments. And note that there are no indication of relationships. Again, we consider this as being anti-symmetry. Why? Because, look, we have values along the diagonal cells, right? We have values along the diagonal cells. So that is a relationship between the same element. Let's say element A here. Let's say put A. Okay, so that there's a relationship A to A, which is itself is only one relation. B to B, C to C, D to D. So there is still one relationship, but there's no reciprocal relationship from the other. Still fulfills the criteria of being anti-symmetry. Yeah. You see, given two elements can only be related in one direction. An exception is for elements at the reflexive line. So the presence of the elements at the reflexive line indicate that it's still anti-symmetry or anti-symmetry. Let's look at the third example. This is obviously anti-symmetry because you see the counterpart, there's no relationship from the counterpart. Only one direction. Only one direction, yeah? Okay, and this one is also anti-symmetry because if it has at least one relation along the diagonal cells, yes, it's considered anti-symmetry because it says here an exception is for elements at the reflexive line. So what are the examples of anti-symmetry in daily applications? Let's look at this. 6 is a number, right? It is divisible by 2 because 6 divides by 2, you get 3. But is 2 divisible by 6? Can we divide 2 by 6 and without any balance? No, right? So it's only one-way relationship. We can divide 6 by 2, but we cannot divide 2 by 6. It's only one-way relation, one direction. This is a valid condition for anti-symmetric. So anti-symmetry is usually considering whether the bottom left segment has any counterpart on the top right segment or vice versa. It can be only one side. Let's say if we have one relation at 3, 1, yeah, cell 3, 1. We shouldn't have any relation for 1, 3. How about if we have we have relationship at 1, 5, then we shouldn't have any relationship at 5, 1. So this is anti-symmetry. It does not have to be only one-sided. Yeah, it can be only any side, but there must not be any counterpart. It can be on any side of the segments, but there must not be any counterpart, right? So let's look at this one. The third example here. It is anti-symmetry because, as you can see on the bottom left segments, right? We have all this, but we don't have the counterpart, similar counterpart on the other segment. Now, what if I shade this part, suggesting that there is relation for cell 4, 5. Does this modification make the anti-symmetry property invalid? The answer is no, because you see, 4, 5, does it have an equivalent counterpart in 5, 4? No, right? So it's still anti-symmetry. So suppose that in the top left, bottom left, and top right segments, there are no relations at all. No relations at all. The only relations that exist are along the reflexive line. And in this example, only one. Does this make it anti-symmetric? The answer is yes. Yeah, because look at the definition again. Anti-symmetric is not symmetric most of the time, except along the reflexive line, if and only if when A is equal to B. So when both segments are empty, check the reflexive cells. If there's any one value, it is still anti-symmetric. Anti-symmetric. Not all symmetry is anti-symmetry. Okay, let's look at example. Not all asymmetry is anti-symmetry. Look at this. R1, relationship R1. Obviously, it is not symmetrical, it's asymmetry because you see, it looks different, right? Imagine you put a mirror here along the diagonal line. By right, both sides, both segments must look similar, but it is not. So it's not symmetry, it's asymmetry. But is it anti-symmetry? What's the definition of anti-symmetry? Anti-symmetry means there are no counterparts, right? But obviously there is a counterpart here. So this is not anti-symmetry. So it can be asymmetry, but still being not anti-symmetric. Okay. You can work out, you can see the same in R2 and R3. They are not symmetrical, asymmetry. They are also, but then they are not anti-symmetric. Usually we have the assumption we may be lured or simplistic simplistically think that if it's asymmetry, it's also anti-symmetry. The answer is no. Anti-symmetry has another criteria, which is uh, to make sure that there's no counterpart. Not even one should have counterparts. I think this slide can help us to wrap up the differences between anti-symmetry versus asymmetry, right? So you see the first quadrant here appears to be symmetrical, but it's anti-symmetric. Why? Because remember the one of the criteria in anti-symmetric, if none of the segments have values, right? Then don't forget to check. Don't forget to check the diagonal cells. If it has any one valid diagonal cells in the reflexive line, then it is considered anti-symmetric, even though there is none in the in both sides of the segments. Okay, and then anti-symmetric can also be asymmetrical, like in this example. You see, it's not symmetrical, but it's at the same time anti-symmetric because both sides doesn't look balanced, right? So look at this quadrant, bottom left. Now it appears to be symmetrical, right? And it's also not anti-symmetric because there is a counterpart. So nothing unusual. But look at this one. This one is not symmetrical, obviously, because when you draw the reflexive line, the bottom left and the top right segments don't look balanced. Yeah. But at the same time, it is not anti-symmetric. Why? You look at this part. The cell 5,4 has its counterpart in 4,5. 5,4 has 4,5 counterpart. This renders it not anti-symmetric. So please revise on this to help you to differentiate between symmetrical and anti-symmetrical. You may be mixing up between anti-symmetric and asymmetric. They are two very different concepts. I mentioned earlier many times. Asymmetry symmetry means that both sides of the reflexive line looks balanced. Anti-symmetric means there should not be any counterpart on either side of the segments, except along the reflexive line. All right, so if given this question where we have only the set defined, so the set here, the name of the set is A, and the elements are 1, 2, 3, 4. Can we identify all the anti-symmetric relations in this set? Okay, so the first answer is all the cells along the reflexive line 1, 1, 2, 2, 3, 3, 4, 4 are anti-symmetric. Okay, and then the second example here, um, 2, 1, and then 3, 1, and then 4, 1, and then 3, 2. Yeah, I'm looking at this one. Yeah, 3, 2, and then 4, 3. Let's look at the red one only. Yeah, ignore the black one because I'm reusing the same matrix from previous relation. So you see, is there any counterpart? The red one's only. Yeah. All right. So therefore, it's anti-symmetric. Yeah. How about the last one? Actually, there are many more. So if I to draw the relation matrix, I'm not going to reuse it because it's already quite cluttered. Let me draw another relation matrix. Okay, because elements are 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so let's look at the third one, third relation. So I start with 1, 2, 1, 2, 1, 3, 1, 4. 1, 2, 1, 3, 1, 4. 2, 3, 3, 4. 2, 3, 3, 4. All right. And let's see whether this is anti-symmetric or not. Again, we always need to have the diagonal line. So you see, there's no counterpart, right? 1, 2, no counterpart in 2, 1. 1, 3, no counterpart in 3, 1. 1, 4, no counterpart in 4, 1. 2, 1, no counterpart in 1, 2. 3, 4, no counterpart in 4, 3. Therefore, it's anti-symmetric. All right. As long as no counterpart. Doesn't matter whether it is on the top right segment or bottom left segment. As long as no counterpart, it is anti-symmetric. So there are a few more examples which you can pause the video and try to work out the solution and then compare with the solution at the bottom. Explanation is already given why it is anti-symmetric, why it is not anti-symmetric. Yeah, you can pause this video and try out on your own without looking at the solution first. Then you can check against the solution. Then do the same for example 3. Again, it is to determine if the relations are symmetric and anti-symmetrics. This one will help you to differentiate between the concept of symmetrics and anti-symmetric. Again, the answer is given in the following slide. Try this on your own. Let's discuss this question because this question is a little bit different from previous examples. Example 4 goes as follows. Is divide relation on the set of positive integers symmetric? So the set of all the positive integers, is it symmetric? All right. Or is it anti-symmetric? Now, one way to analyze this is by drawing the relation matrix. But here we are talking about positive integers, right? So there are many positive integers, isn't it? We don't have to draw all of them. We just draw a few as samples. In this case, the example here is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, so let's think. Divides. Yeah. We can divide 1 by 1 against 1. We can divide 2 against 2, 3 against 3, 4 against 4, 5 against 5. That's why we plot them. We plot all the values in the reflexive line. So this already fulfill anti-symmetry, but not enough. This is just one of the criteria. Doesn't have to be all cells in the reflexive line needs to be having the value 1. Even 1 is sufficient. But we must make sure that there are no counterparts on the segments, bottom left or bottom right. There are no counterparts. All right. So let's think about it. 2 can be divided by 1. 2 cannot be can be divided by 2. So let's go row by row. Let's begin with first row. Yeah, sorry. Let's begin with first row. Row number 1. 1 can be divided by 1. 1 cannot be divided by 2. 1 cannot be divided by 3. 1 cannot be divided by 4. So we leave them empty. 2 can be divided by 1 and 2, but the rest empty. 3 can be divided by 1, cannot be divided by 2, but it can be divided by itself. Of course, it can be divided by 4 and 5. Then we repeat the same for number 4. 4 can be divided by 1, can be divided by 2, cannot be divided by 3, but it can be divided by itself. 4. 5 can be divided by 1, cannot be divided by 2, cannot for 3, cannot for 4, but for itself. Now, having drawn this relation matrix, now analyze. Okay, we have all the we have all or some in the diagonal line. Let's say if we don't have, it's also fine. It's also fine if we don't have. Yeah. And then the most important part is to check the counterpart. Yeah. 2, no counterpart. 2, 1, no counterpart. 3, 1, no counterpart. 4, 1, no counterpart. 4, 2, no counterpart. 5, 1, no counterpart. So this fulfill the criteria. This has fulfilled the criteria of being anti-symmetric. So yes, we can conclude that it is antisymmetric. It is antisymmetric because if A and B are positive integers with A divided by B and B divided by A, then A is B. So the only time when A can be divided by B and B divided by A, yeah, is only along the reflexive line. This will be an exception when it is itself. Okay, so let's look at this question and see whether you can just analyze from the set of numbers and determine whether it's reflexive or not. Of course, the traditional way, as I have taught earlier, is by drawing the relation matrix, but it may not be convenient or time-wise to do so. Sometimes, if the question does not require you to draw the relation matrix, you can actually tell easily. We are working on what set? An anonymous set, and what are the elements? 1, 2, 3, 4. So reflexive line is 1, 1, 2, 2, 3, 3, 4, 4, right? But look at this relation. It is missing 4, 4. So it is not reflexive. Okay. And then why is R 1, 2, 2, 1, 3, 1 not symmetric? So if you look at the relation matrix just now, the mirror or the counterpart is always flip. Yeah, like for example, 1, 2, the counterpart is 2, 1. 3, 1, the counterpart is 1, 3. But is there 1, 3 in this relationship? No, right? So obviously, 1, 3 is missing. Therefore, it is not symmetrical. Symmetrical means you must have counterparts. As anti-symmetric, no counterpart. Asymmetric, you can have some with counterparts, some without counterparts to become asymmetric. Mind you, and asymmetric and antisymmetric are two different concepts, even though they look very, very confusingly similar. Okay, let's move on to a different property of relation now. This property is called transitive relation. Transitive relation requires us to determine if all, okay, the keyword here is all, for all the elements of A, okay, if we have AB and we have BC, is there AC or not? So let's look at one analogy. We are we able to get from Penang to Ipoh? Georgetown, Penang to Ipoh? Yes, right? Can we get from Ipoh to Kuala Lumpur? The answer is yes. So, can we safely assume that we can get from Penang to Kuala Lumpur? The answer is yes, right? So, again, let's break this down. We can get from Penang to Ipoh. We can get from Ipoh to KL. Therefore, we can get from Penang to KL. We are looking for this pattern for all the members of the set. Yeah, we are looking for this pattern. So we are going to put it this way. If there's order P, I, there's an order I, K, L, then that should be P, K, L. Right? So we are looking for this pattern. Now, wherever you see question asking you to analyze whether the relation is transitive or not, this is what you can do. I recommend you to draw this table, whereby the first column, you put it there, pair AB, the second column, pair BC, and then an arrow, which suggests that there should be A to C. You see? A, C. The common element is B. So the common element actually connects A to C. You see that? So prepare this table. All right. Then after that, we'll be looking at the relation. Yeah, this is relation. This is another way of writing relation. You can write this way, Or you can write this way. All right. So you check one by one. VA. Okay, so we can put VA. Okay, we have B to A. Let's find in the relationship. If we have B to A, the common here is the connector here is A, right? So you see in this example, the connector here is A. So do we have A something here? Or we have AD? So if we have AD, then do we have BD? Okay, we managed to find BD, right? So yeah, this is transitive. But we're not done yet. We are just done with the first BA. We must proceed with AD. Okay, then we look. Then obviously the next one is D because this is the connector. D with something else. Do we have D with something else? None, right? So because we don't have D with something else, we can skip this part. Okay, we can skip. And then we go to BD. So obviously the next one will be D something else. So there's no D something else, right? So again, we can skip. So there's no proof of non-transitive. Therefore, it's transitive. Okay. So let's look at some examples. You can try out on your own. You can pause this video and you can test with this relation. Okay. You can also test with this relation. Yeah, to find out if it is not transitive. But because I have a few more examples, I will jump to those examples. Okay, this is a transitive example. Now, when you are given this question, and the keyword here is that you need to be able to verify if the relation is transitive. So look out for the relation. So relation here is 1, 1, 2, 2, 3, 3, and 1, 2. And then the is from the set A. So we only need this. Yeah, we only need this information. So the moment you see this, you prepare a table like this, whereby we have AB, BC implies AC. So we start with 1, 1, 1, 1. So we take the second part of the order of the pair. So we look if there's one something else. 1, 1, 1. Okay, there's 1, 2 here. So if there's 1, 2, that means there should be, we should take this 1, take this 2. Is there 1, 2 or not? Yes, we can find 1, 2 again, which is similar to this, right? So, okay, this is transitive. Now, 2, 2. The second one, 2, 2. So 2, 2 obviously will be 2 something else, you know. But because here, you see 2 something else is again itself. And obviously, it is suggesting that the AC is 2, 2 as well, right? Which again, we can find itself. We can find itself. So it's transitive. 3, 3 is actually of the same nature as 2, 2. So we can actually easily skip this because you know for sure it's transitive, right? So we are done with 1, 1, 2, 2, 3, 3, and finally 1, 2. So look at 1, 2, 1, 2, and then the connector is 2, right? So we look up here. Wait, any of the pair is 2? Yes, 2, 2. So 2, 2. So we're expecting 1, 4, 1, 2 to occur, which yes, there is 1, 2. So it's transitive. Okay, so we have checked 1, 2, but 1, 2, and then 1, 2, and 2, 2. Is there any more? Let's say, is there possibility like 1, 2, and then 2 something else? Okay, 2, 2, we already checked it. So no more already, right? So we have tested all of them. And so far, all of them are transitive. Therefore, the relation is transitive. All pairs have been tested. All of them are transitive. Therefore, the relation is transitive. So this is another example. Check whether this relation. So this relation is a different relationship from the one just now, and this is how we check it. All of them must be transitive for all the relations in order for the R to be transitive. All of the pairs must be transitive in order for the R to be transitive. Okay, so I'm not going to go into the details of this example 2. I want to go into details of example 3 because this is the example where the R is not transitive. So it is a different relation. Yeah, we have a 1, 1, 2, 2, 3, 3, 1, 2, 2, 1, 2, 3, 3, 2. The first thing you do when you see the word transitive is to draw this table. A, B, B, C hints or implies AC. All right. So let's start with 1, 1. Okay, so I put 1, 1. So obviously the BC is 1 something else, right? So 1 something else. So this fulfills the criteria. 1 something else. So it's 1, 2. So is there 1, 2? Again, fulfills the criteria 1, 2. And then we move on to the second one, 2, 2. 2, 2. Okay. So you see, because we have 2, 1 here, right? Part of 2, 2. We know if 2, 2, 2, 2, 2, 2 is definitely transitive, but we also have 2, 1. So we're going to skip 2, 2 because it's obvious. So we're going to put 2, 1. And then therefore 2, 1, we take this value and take this value. So it should be 2, 1 here. Okay. So it's transitive. Then we move on to 3, 3. Okay. 3, 3. So we take the 3 here. We put it here. 3. Is there any 3? We have 3, 3. So 3, 3 is itself, right? Obviously it's going to be transitive. So we're going to skip this part. We're going to use 3, 2 instead because this one also fulfills the criteria. Yeah. So 3, 2, we put 3, 2 here. And it implies that there should be 3, 2. Okay. Pass. Then from 3, 3, move to 1, 2. Okay. So the connector is 2. So we have few possibilities here. See? 2, 2, 2, 1, 2, 3, right? So we're going to test each of them one by one with 1, 1, 2. Yeah. First, we're going to test with 2, 2 first. So 1, 2, 2, 2. So it implies there should be 1, 2. And we can find 1, 2 here. Okay, pass. Again, we cannot move to 2, 1 yet. Yeah, because we still have to check 2, 2. We have checked 2, 2, but we haven't checked with 2, 1, right? 1, 2, 2, 1. So therefore 1, 1. Okay, we can find 1, 1 here. So it still passes. Can we move to 2, 3 yet? Still cannot because we haven't checked with can we move from 1, 2 to 2, 1 yet? No, cannot because we haven't checked with 2, 3 yet, right? So 1, 2, 2, 3, therefore 1, 3. Okay, let's check whether there's 1, 3 here. 1, 1, 2, 2, 3, 3, 1, 2, 2, 1, 2, 3, 3, 2. See, there's no 1, 3, right? So the moment you find one instance or one row where it is not transitive, we can stop. We can stop and we can say that the R is not transitive. The R is not transitive. The moment we find one instance where it is not transitive, we can stop. We don't have to proceed already. But to prove that it's transitive, we have to keep on testing until all are tested. So you can pause at this. You can pause this video at this slide and try out the following relations by drawing the table just now and determine whether R1 is transitive or not. Then you draw on a table for R2, determine whether it's transitive or not. And the same goes for R3. The answer is already given. Yeah, not transitive, not transitive, not transitive. See whether you can get the same answer as this one. If not, you can look back at the examples because they are sufficient to help you to learn how to analyze the transitive property of the relation. Okay, I would like to talk about this exercise. which I would like you to try now. You may want to pause the video here. This exercise is interesting because instead of working with numbers, we are working with some daily life context. Yeah. For example, A is taller than B, assuming A and B are people. Yeah. R, the relation R. Let's look at the question. The relation R is the set of all people that you can imagine. Okay. Check whether the relationship, check whether A and B, which are people, for the relationship R, relationship A, relationship B, relationship C and D, whether it is reflexive, symmetrical, anti-symmetrical, or transitive for each one of them. So this is going to be taking some time. Yeah, this is going to be taking some time. So you may want to pause here and try to work out the solutions for A, B, C, and D. Then we will discuss. You can continue the video once you're done. All right, let's look at the answer for A. The relationship is A is taller than B. So is it reflexive? Recall the meaning, the definition of reflexive. Reflexive is comparing against the same person. Yeah, comparing against the same person. In this case, imagine yourself. Can you be taller than yourself? Cannot, right? So it is not reflexive. Is it symmetric? If you look at your friend or somebody in your house, maybe your brother or sister or your parent, are you taller than them? If you're taller than them, are they taller than you in return? It cannot be, right? If you're taller than them, then they must be shorter than you. If you're shorter than them, one of them, then that person is taller than you. It cannot be symmetrical. Is it anti-symmetric? Again, yes, because you cannot have a counterpart, right? If you're taller than your sister, then your sister cannot be taller than you, right? So it's only one way relation. And then, is it transitive? Let's say if you are taller than your younger brother and your younger brother is taller than your baby brother, yeah, then you are taller than your baby brother. Does this make sense? Of course, it makes sense. You are taller than your younger brother, and your younger brother is taller than your baby brother. Therefore, you are also taller than your baby brother. So it's making sense, right? So it's transitive. Let's move on to relation B. A and B were born on the same day. If you're born, think of it. Can you find somebody in the world who has the same birthday as you? Sorry. That one is for the other question. Reflexive is referring to yourself. If you imagine yourself, you think of your birthday. Yourself, if you have birthday on a certain date, yourself will have, I mean, no matter how ridiculous it sounds, right? You and yourself will have the same birthday on the same day, right? So yes, reflexive, yes. Transitive, sorry, this one is not transitive. This one should be symmetric. It's a typo error. Symmetry. So think of a friend who has the same birthday. If you have birthday, let's say on August 31st, and your friend also birthday on August 31st, obviously it's symmetrical, right? Same. So yes, it's symmetrical. Antisymmetry. It is not anti-symmetry because anybody can be born the same day. It's not like I'm born on 31st of August, then you cannot be born on the 31st of August. So it's ridiculous, right? So anti-symmetry is no, it's not anti-symmetric. Transitive, yes, if S is born on the same day as Y, who was born on the same day as Z, then S is also born on the same day as Z. Think of two other friends who share the same birthday as you. You are born on, let's say, 31st of August, your friend A, 31st August, friend B 31st August. So if you're born on 31st August, then friend B is also 31st August, right? So this is transitive, yeah? Because you and your fellow, your friend A, and your friend A and friend B, and you yourself with friend B. So this is you and A and B, therefore you and B. So it's transitive. Okay, A has the same first name as B. Okay, think of your own name, first name. Can you find somebody with the same name as you? First name, not the family name. Easily you can find, right? Yeah, they might, or even if you don't have, think about it. There are so many people in the world. You can easily find somebody with the same first name, right? So it is reflexive. It's reflexive. You yourself, you have the same name. You and the other person will have the same name. It is not anti-symmetric because it doesn't matter. You have the same name. The person can also have the same name, right? You cannot be like, I already have the same name. Then you cannot have that name. No, it's not anti-symmetric. It is transitive, yeah. Because let's say you have three people having the same name. Not impossible. A and B have a common grandparent. Reflexive, yes, because you and yourself, yeah, reflexive is always comparing against yourself. Definitely have the same grandparent. Symmetric is think of your brother or sister. Don't you share the same grandparent? So it's symmetric. It's not anti-symmetric because it cannot be like you have this grandparent, but your brother or sister cannot have this grandparent. Yeah, it's not just one way. It's possible to be two-way. And then transitive. Okay, transitive is the answer is no for transitive. Why? Think of this. You and your cousin can share a grandparent, and your cousin can share their other grandparent with somebody with someone else who is not your cousin. Right? So you will not share a grandparent with that someone else. Can we graphically display this? Let's say this is you. This is your cousin. Okay, these are your parents, father, mother. Okay, and then your cousin, we have his or her mother and father. And this mother and father could be siblings from the same grandparent. Okay, and then your cousin may have another um, relative. Okay, with his or her own mother and father. Okay, and maybe the father and the mother share the same grandparent. Okay, so you and your cousin share the same grandparent. Your cousin and another relative, distant relative, share a different grandparent. So can you say that you and that distant relative share the grandparent? No, right? So it is non-transitive. Okay, for each of the following relations, on set 1, 2, 3, 4, decide whether it is reflexive, symmetric, antisymmetric, and transitive. So I hope you will do this activity on your own. You can pause this and see whether you're able to figure out how to come up with the solutions. Yeah, so for question number 1, there should be reflexive, symmetric, antisymmetric, and transitive. The same goes for R2, R3, R4, R5, R6. It's going to take some time for you to work out on. So Let's move on to the next concept, which is equivalence. Equivalence is when the relationship has fulfilled three criteria. It must be reflexive, symmetric, and transitive. If it fails any of these criteria, it's not an equivalence relation. Let's look at this by example. Example 1. Given the following relation matrix R1, okay, determine whether it is an equivalent relation. First, you need to check whether it is reflexive. So let's look at the diagonal line. Okay, not reflexive. So it fails, right? It's not reflexive. So immediately you can say not equivalent, not an equivalent relation, because it fails at reflexive. It must not fail at any. Now, determine whether the following is an equivalent relation. So this is a different relation matrix. Check the first one. Is it reflexive? That's the easiest one. Yes, it is reflexive. Then check whether it's symmetrical. Okay, it looks symmetrical. Now, is it transitive? Is it transitive? So let's say I put it this way: A, B, C, D, A, B, C, D. So we have to immediately draw this table. So we have a AA, because you see. So again, we have A here. Then the only relationship that has A is AA, and apparently it has to be AA. So this is transitive. Then we move on to the next row, B, BB. So obviously it'll be BB, BB, transitive, CC, 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 transitive, D, 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 D. Okay, all is transitive. You see, we have tested all the possible relations already. All transitive. So fulfilling the reflexive, symmetric, and transitive properties make it an equivalent relation. Let's look at example for relation 3. Now, first, the easiest one to check whether it's equivalent or not is to check whether it is reflexive. Yes, it is reflexive. Is it symmetrical? Yes, reflexive, symmetrical. Is it transitive? Okay, so this is the tougher part. Let me clean up this part. Right. A, B, B, C, dash, A, C. Okay, let's go row by row. Let me make it this way. A, C, D, A, B, C, D. So let's go row by row. Okay, so apparently this is going to be long, but you can stop immediately when you discover any one that is non-transitive. So we will start by AA. So apparently AA is always transitive. So I will skip AA, yeah? AA is always, all these AA, BB, CC, DD is always transitive. So I'm going to make my life easier. So I straight away jump to A. AA, okay, skip, because it's definitely transitive. And then AB, which is this one. So is there B something else? Apparently they are BA. So there should be AA, which is itself, okay, transitive. But we are not done yet. We're still looking at AB, which is this guy, AB. Then the next fellow is BB, right? BB. So we take this A and this B. Is that AB or not? AB, yes, there is. So it's transitive. So we're not done yet. We're still looking at AB. So far, is it AB, AB, AB? We're not done yet because we still have to test with others like BD. See, because BD is valid, right? We skip BC because BC is not existing. We look at BD. So we expect to be having AD. So let's go to A and D. See, D here, AD does not exist. Not transitive, right? So we can stop. We don't have to do the rest already. We say that R3 is not transitive. So since R3 is not transitive, it's not equivalent. Yeah. So don't have to be afraid. Transitive it may look tedious, but the moment you find non-transitive, you can stop and can conclude that the relation is not transitive. Therefore, the whole thing is not equivalent because equivalent requires it to be reflexive and symmetrical and transitive. Let's go through the summary. We have learned about relation, which connects the elements of sets. Okay, it's actually the arrows that connects the elements of set. If only two sets are involved, then it is called binary relation. Yeah. A function is a type of binary relation. A function must make sure that it only has one output. That means only one element in the codomain. You can have multiple elements in the domain, but the element in the codomain in the mapping must be exactly 0 or 1. And then number 3, we can represent relations graphically using relation matrix. Why relation matrix is good? Because we can do a lot of analysis. What kind of analysis can we do? We can analyze properties of relations such as reflexive, symmetric, antisymmetric, or antisymmetric, and transitive. Yeah, we have learned that reflexive is checking along the diagonal line. Symmetry is checking the segments on opposite ends of the diagonal line to see whether they are similar, balanced or not. Antisymmetry is whereby we need to be sure that all the ordered pairs, the relationship only occurs in one direction. So there's no counterpart on the other segment. And transitive is where we use the table to establish transitive relation. Let's say we have a relationship between A and B, relationship between B and C. There should also be relationship between A and C. If it fails, then the whole relationship is non-transitive. And then to determine ultimately whether the relationship is equivalent or not, we have to make sure that it is reflexive and symmetric and transitive. So thank you very much for giving me your attention. I hope you have benefited from this lecture. Thank you very much.